Robot Talk is the podcast that sits down with robot enthusiasts from around the world and asks them the questions you always wanted answered. Like, does the drone know where it's going? And how does that thing work? Hello everyone! Welcome to Robot Talk. I'm your host, Claire Asher, and this week's episode is all about how robots view, perceive, and navigate the world around them. I'm finding out about the latest advances in vision for small aerial drones. Before we get started, please remember to like or rate this episode and leave us a review if that's something you can do on the platform you're listening on. And don't forget to share the podcast on social media or tell your friends about it. It really helps us reach more listeners, so thank you in advance. So, without further ado, I'm excited to introduce this week's guest. I recently had a fascinating discussion with Margarita Chli from the University of Cyprus, all about vision, navigation, and small aerial drones. This week, I'm talking to Margarita Chli, a professor in robot vision at the University of Cyprus, whose work focuses on advanced robotic perception for small aerial drones. Hi Margarita, lovely to have you on Robot Talk.
Hi Claire, thanks for inviting me and well done for pronouncing that surname so well. It's not easy.
Thank you. So you're the director of the Vision for Robotics Lab at the University of Cyprus and ETH Zurich. So can you tell us a little bit about the lab and some of your current research projects?
Yes, sure. So at the Vision for Robotics Lab, we are split between these two locations, University of Cyprus and ETH in Zurich. And to put it simply, our aim is to teach robots to see and to collaborate.
Okay.
And maybe I can give one example of our latest project that was approved. So this is an ERC Consolidator Grant. It's from the European Union to work on blue sky research in general to advance robotic perception. And our aim is to automate drone navigation in difficult scenarios and address some of the fundamental questions, some of the fundamental problems that we have in that, in order to be able to address basically all the issues of robustness and unpredictability of the world around us that we humans are very good at compensating for.
Yeah.
But pre-programmed robots have issues to deal with.
Mm-hmm. So you said teaching robots to see. What kind of learning component is there in this?
Yes, teaching, in this sentence, I used it more loosely. So there is some machine learning involved, of course, but we also work with handcrafted methods as well. We are trying basically to see where do techniques perform their best. So some learning-based techniques, for example, are very good with processing of images of the same location over and over again, depending on different weather conditions and different seasonal changes. And machine learning seems to perform very well. When you want, for example, to recognize a place that you have been to before and you have a slight change in viewpoint, then geometry starts to become more important.
Right,
and that's where the fusion of handcrafted methods that are able to recover the geometry of the scene, they start becoming also more important. So, I focus now a little bit on the machine learning versus non-machine learning. But as I said, we use this teaching robots to see is a loose term to say basically that we work on developing vision-based perception for robots.
Okay, yeah, that makes sense. And you mentioned difficult environments, I think was the phrase you used. Can you talk a little bit about what makes an environment difficult?
A real environment is by definition difficult for a robot, and meaning that anything that is outside a controlled laboratory environment where you can control the illumination or wind gusts that you might be having, even more so when you start thinking, I want to have my drone, for example, to navigate from point A to point B. What is there that I can encounter that can confuse me. And you can have a set of factors, but what if it's raining? What if there is a fire in the way and there's smoke?
Yeah.
What if there's dust? So it's basically, these are what we call perceptually degraded environments with lack of good illumination, where vision doesn't perform as well, and also other sensors don't perform as well. So these now are deemed to be some of the biggest challenges that robotic perception is dealing with. And one of the biggest hurdles before we are able to employ robots in our general everyday life, if you'd like.
Yeah, vision is something that's so intuitive to us as humans. We do it without thinking.
Absolutely.
And when you really start to break down like what it actually involves, it's like, wow, actually, this is an incredibly complex skill to try and impart on a artificial system.
Absolutely, absolutely. And we have, in many ways, a very sophisticated visual perception system in humans.
Yeah.
With a limited set of cues, we are able to interpret a situation because we are interpreting with vision, with previous experiences, with things that other people told us. And so there has been learning throughout our lives that we're incorporating into this decision-making process.
Yeah.
And yes, perceiving the world through a camera lens per se, I'm trying to decode what these pixels, which are basically numbers, what these pixels are depicting, is a very difficult task indeed.
Yeah.
And I do talk a lot about vision because it's the main sensing modality, the camera that we use in the lab.
Yeah.
But again, this is something that has become a little bit of a loose description over the years because we start looking at different types of sensors that can equip our robots with this ability to see. So it could even be LiDAR scanners or what we call event-based cameras that have they trigger different pixels firing depending on whether they are changing their illumination.
Okay.
So there's a whole set of sensors that the community and also my lab is working with.
Yeah, at the moment I'm reading a book by Ed Young called An Immense World, which is all about animal senses. And there's an awful lot of senses beyond just vision that can help you kind of create like a spatial map of the world around you that we don't really think of as vision because we can't do them. But of course, robots can.
Yes, and you know what? I've been in this area for what I lost count. About 20 years, a bit less.
Yeah.
And the field has changed so much. So when I started, to be able to have a camera processing in real time, the video feed was a big thing. But by now, we have reached this level of maturity that we start realizing that one sensor alone will not be the answer.
Yeah.
So we would need to have some clever sensor fusion techniques to see which sensor to trust and when. And for example, this is one fundamental question that we're trying to address in the lab. Of course, it depends on the setting, right? And then the drone or robot would automatically detect which sensor to use and when, depending on the application that it finds itself in.
Okay. So do you kind of take inspiration from the natural world at all in your work?
Yes and no. So I think there's a school of bio-inspired vision, computer vision, and my work doesn't fall within that, but I definitely use inspiration from, humans can do it, so it is possible.
Yeah.
How do ants navigate the world without being able to see everything from having the scene overview, but they are able to find their path and return back to their nest, So from a high-level perspective on capabilities, there is a lot of influence. But looking at the history of computer vision and how it has evolved, I think we see that the top performing systems work in a very different way than what nature has evolved to be doing, basically.
Yeah.
And I guess it does depend on what kind of sensors you have on board and what kind of body of a robot or animal you're talking about, right? But I think, thinking now in terms of sensors that we are using, and we're always looking at the next best sensor that is out in the market and let's try it. I think there's a lot of bio-inspiration there as well, on seeing, here's another way of perceiving the world that, humans were not good at doing that, measuring distances, for example, like the LiDAR scan is doing, measuring distances at almost an instance. But using this information, what is it that you can teach your robot about the world?
Yeah, I was learning about how bees can use polarized light to navigate, which is obviously not something humans can do, but maybe one day robots could.
Yeah, I mean, there's so many creatures that are incredible, right? Bats, for example, right? Or even ants. There was, I had a colleague, he was working with ant navigation, and they were really showing how ants are able to localize themselves by building a set of signatures of the horizon at different places.
Yeah.
Because, again, they don't have the overview of the scene, so they look at the world from, really low, close to the ground, and they don't see that many features that we would think are distinctive. But somehow they manage to return back. Of course, maybe there's not just vision that they're using.
Yeah, and I guess, with drones, you've really got the kind of the bird's eye view that you're trying to use to localize.
Absolutely. And maybe one more thing that I think it's important to highlight, because here now that we're talking about bio-inspiration, I think it's also related. We are teaching robots to see, but also to collaborate, because we realize in the same way that sensors, there's no single sensor that will win over every other in every application.
Yeah.
Then we start realizing that if you want your search and rescue operation to be mapped by a set of robots, you're better off using 2 or 3 robots, and even with a different viewpoint and different capabilities. So having a heterogeneous team of robots would be a good way forward. Now, I think there have been a lot of projects and a lot of talk about it. We are still, I think, scratching the surface on what it is that we can do with robotic teams to do that. And I have seen a very nice example of how ants are building a bridge to bridge gaps between 2 sides of whatever it is that they want to go to. And I use this as an example of, look at how collaboration can win over this unsurpassable, otherwise, challenge for a single agent by themselves.
Yeah, absolutely. So you've achieved some world firsts for Robot Vision, and one of those was the first demonstration of collaborative robotic perception for a small swarm of drones. So can you tell us a little bit about that?
Yes, sure. Yes, at the time I was starting off my lab at ETH in Zurich, and rumor had it that Google is working on having multi-agent mapping module being released soon. And I was thinking, they've done it all. What's left for us to do? But then I'm glad that we went ahead, because in the end, the final result was very different. So we started thinking of the problem in a logical manner. So if we had all the resources in the world, how would you have a team of 3 drones collaborating with each other to map their environment and localize themselves inside this environment? So ultimately, you want each agent to be independently autonomous. But we know that this autonomy has its limitations. So you cannot keep track of all of your past experiences because you have limited resources on board.
Yeah.
So we thought that, let's just keep track of the most recent horizon of experiences. And before we forget what has happened in the past, just send them up to the cloud or down to a desktop machine. And then the desktop machine would act like a bookkeeping entity to do the more cumbersome tasks, more computationally demanding tasks. And then if, for example, there's detection that two drones have experienced overlap inside the trajectory, then why not correct for this error that you obviously would have if you get more information and you start rethinking how your map should have been. And then you can inform all of the participating agents and participating drones of any changes that this would mean in their own local map.
Okay.
So, we carved out this system and then tried it multiple times to make it work in reality. And I'm very glad we pursued this direction, despite, it's a constant problem, if you'd like. If you are in an area like Robotic Vision, that you have top labs in the world and top industrial entities in the world also working on similar problems.
Yeah.
So it creates, it's this ecosystem that is evolving very fast and it's fascinating. And it can also be stressful because you always feel like, oh, I need to keep up. We need to keep. But at the same time, there's the good old focus on your problem kind of mentality that in this case, it paid off. So yes.
Yeah. It's interesting that the drones didn't need to communicate directly with each other. They just needed to communicate with that kind of base station computer.
Yes. In this first example, as I said, we tried to simplify the problem as much as possible.
Yeah.
So we used the centralized approach. Now, since then, we are working on having a more peer-to-peer communication to have a more scalable solution, because obviously this is, the fact that all data has to be processed by the central server can become a limitation if you want to talk about 70 agents, 700 agents, I don't know what. Then we are now also working on a distributed system where we are thinking, what if every agent just talks to their neighbors?
Okay,
and the neighbors just talk to their immediate neighbors. So the information would be there inside the network, but you would have to, at least in my brain right now, it feels like you would have to propagate the message to the ends of your network and let that message come back to you to understand really, to get some global information about what is happening with the rest of the swarm.
Yeah, that's really interesting, like information kind of diffusing through the network.
Yeah, and then that's where I don't really know how biology is dealing with that. But somehow it's also interesting to see, this flock of starlings, they're flying around and they're following each other. And I don't know if they're crashing into each other. No, but they seem to be recovering.
I think that they do something similar. They just pay attention to their nearest neighbors and use quite simple cues, and it kind of just creates this amazing emergent behavior.
Exactly. Yeah, so there you go. Inspiration again from biology and capabilities.
I was going to ask you about scaling up and whether that makes the task easier or harder. I guess maybe a bit of both.
Yeah, well, I would say harder, but the word that comes to mind is fascinating.
Yeah.
In academia, we like to work on harder and harder problems. That this is the fascinating bit. Let's do everything with one camera and let's do everything with that many agents. That is not possible right now. So yes, because what is exciting is the possibilities that this opens up, right?
Yeah.
So how nice would it be if we had the algorithms that they're able to adapt according to the size of the swarm that you have available? If one of the agents, drops out, gets lost, then you don't lose where, the goal of the swarm is going.
Yeah.
Or even, to project to this idea that I mentioned before of having a heterogeneous team of robots.
Yeah.
To be able to use a ground robot for the heavy processing, to use the drone for navigating through the small openings and gaining the overview of the scene. So I think this is a very good, or intuitively, it feels like the right way to go for multi-robot perception. But yes, I describe this and it's probably, I'm describing the PhDs of 100 people that have to go into that to make something like this happen.
of course.
Mm-hmm.
And so what do you see as some of the real world applications for these kind of advances in robot perception?
Yes, good question. Good question, because I think whenever I give a talk to audience they're not engineers, they're not scientists. When I talk about drones, I feel the room temperature going down. We talk about military applications because, to be fair, that's also the first time I saw the word drone. It was in an article about some war.
Yeah.
So it became my thing to advocate for all the amazing things that advancing robotic perception can do for humans, all the good things for humanity that this development is promising. So from search and rescue, we had this huge disaster in the Fukushima power plant, where it was a perfect example where we didn't want to send people on site because there was radioactivity, so we would expose them. We had to expose them to all these hazardous environments. But at the time, robotics was not there yet. We didn't yet have the team to be able to do that. And come back with useful information and have the onboard autonomy to be able to take decisions on where to look next. So search and rescue, monitoring of construction sites, is this building being built according to the CAD model, or what are the deviations, or in general, monitoring and even maintenance of large infrastructure, power plants or wind turbine farms that we know that they're also hazardous environments for people to go and inspect. Monitoring of wildfires is one of the topics that I'm particularly interested in. Again, driven by both the intellectual interest that it's very difficult to have visual perception in smoky areas. And, you have a constantly evolving, very dynamic environment, but also from a humanitarian perspective, right? So wildfires have started dominating our news outlets every summer. It's becoming crazy. So, and then many friends of mine who are not into science, they're asking me, so what are your drones doing? Could you send some of them to help out in Greece? Or so really being driven by all these problems. And even simpler things like scanning archaeological sites. So archaeologists would like to know how archaeological sites are being influenced by earthquakes, by natural phenomena, having this ability to click a button and have your swarm of drones navigate around the Parthenon and give you a 3D reconstruction in XY accuracy, I don't know what, to start, building up a model of how things are degrading. And of course, gaming. If you have a 3D model of your scene, then why not gaming?
Yeah, absolutely. There seems like a huge number of possibilities. Right at the beginning when we started chatting and you mentioned like navigating in smoke-filled environments, I thought immediately of the wildfire applications.
Absolutely. Unfortunately, we have a long way to go, but nevertheless, we have to keep trying, and there's so much that robotic perception can do to help out in these situations, to surpass what humans can do in terms of perception. That would be one great example that we could assist in enhancing our standard of living.
Yeah, absolutely. It seems like a really exciting, dynamic, fast-paced place to be working. So
exactly. I'm glad this comes through. I guess you're also naturally interested, but I'm also naturally very excited about this.
Yeah, it's really cool. Margarita, it's been great chatting to you today. I've been speaking to Margarita Chli, a professor in robot vision at the University of Cyprus. Thank you.
Thanks.
Thanks for listening. If you enjoy Robot Talk, I'd really appreciate it if you could share the podcast and leave a review to let us know what you think. And don't forget to enter our competition for a chance to win your very own Robot Talk t-shirt. For more information about the competition and how to enter, check out robottalk.org. Next week, I'm talking to Mario De Castro from CERN, all about robotic inspection and maintenance in hazardous environments. Until then, I've been Claire Asher, and this has been Robot Talk. Robot Talk is brought to you by the Hamlin Centre, Imperial College London.